Um, Hello, I'm Supratim. I'm from the beautiful city of Hamburg. I work in the lab Cozy Bio. We work on different things, different kind of data, ranging from genomics to EHR, health record data. We use different kind of algorithms. But personally, I work on deep learning models. So what I'm going to present is our tool called DB Converter, which is a self-supervised generative AI that enables conversion of two non-overlapping cohorts. So basically what you're doing is we're solving the data incompatibility problem for non-overlapping data cohorts. Now, many of us here work with different kinds of data. Some we have seen many talks on multiomics, some in EHR, some are health survey data. Although there are different data cohorts, many times they are actually trying to measure the same underlying common reality that sometimes can be the health status. The is this person does this person has type 2 diabetes or not? Now, even inside the health survey data cohorts, this is the data I personally work on. There are many different data cohorts, and all of them are trying to assess some kind of health status of this person. However, they are not really compatible. And the incompatibility of this data cohorts comes from the fact that each data cohort has different features. So you go to one hospital, you fill up a survey, they do certain tests. You go to another hospital, they do some other kind of test and another different set of questionnaires, right? And so the reason is different instrument and different questionnaires. And this can also be used, is common for other areas like multiomics. You might use two different devices, and then you get different set of data, and then you don't know how to merge them. And although it's different, but they both are trying to measure the same underlying reality just from different perspective, right? So why does data compatibility matter? So for all of us here, who are data scientists, we want to gather the data together, make a big database, and use that for training a model. Many times that's better because you have more data, right? Sometimes you have trained already a model in one of the data sets. You have another data set and that has different variables, and you cannot use the already existing model. So it would be useful if you could convert your database to the in the format of the pre-existing one and use the existing model. So this is what we are trying to solve. Now, the current paradigm of database integration only works, and there are multitude of papers, especially in multiomics, of database integration using deep learning, autoencoder architectures. But all of them has one thing in common. You need enough amount of common samples that are in both cohort. So you want to see if a patient goes in hospital A and hospital B, how the same patient looks in both of them. The problem is we don't have this many times. So the usually you do is you have this common patients for both of them. If you can find enough of them, you can train a supervised deep learning models on these overlapping samples, and then you use this model for the non-overlapping ones, map them, and integrate them. So this is the current paradigm. Bigger problem, many times we don't have enough or sometimes no overlapping linked samples at all. So our goal was to, can we even still do this? Because here we see that there is no ground truth to train on. We need to have the y and the predicted y and calculate the loss for each one so that we can train the deep learning. That's how the field of deep learning works. However, we don't have any ground truth here. So our aim was to design a solution that would convert one database to another, and it would not require the traditional way of doing it with the ground truth or overlapping samples. And as I said before, we cannot use the traditional supervised learning for this. So we present our tool DB Converter. So to do this work, I work with synthetic, continuous and categorical data, and also some real health survey data, because that's what I personally am interested in and my PhD is focused on. So we used one from EU, survey for health, aging, and retirement data. We use one from Germany, German aging survey. Now, if you pay attention to the name, you see the aging in both of them. So both of them are trying to measure some health aspects of aging populations, but they use different questionnaires, different data formats. So the DB converter is a tool that uses the knowledge of traditional deep learning and also the field of category theory. And the underlying idea how DB converter works is that it preserves partial order among the samples in latent dimension. What does that mean? I'll come to that in a bit. So imagine you have two databases, and each database you can think of it as a category. The category is a mathematical structure that has objects, that has elements, and the morphism in between the elements. So here, let's think of each patient as one of those elements inside the category, and the relation between them, the morphism, is less than equal to sign, and that's what I'm calling partial order. So let's say it's the level of physical activity. So in one database, one patient is more active than other. So you can range them in order, right? So we can do that in both of the database. So if you want a mapping function, what it should do is it should preserve the order. So by the way, this way of ordering set, we call this a post-set category or partially ordered set category. Now, a good map would map the most physically active patient in database A to the most physically active patient in database B. So that's the basic principle in which we work on. Now, what I told you is just in one dimension. If you would actually have a one-dimension problem, you can do it without any machine learning. However, the problem is that we have a high-dimension problem. So think of it, we have in some latent space, there would be an order. And so these are the patients, and the arrows between them actually represents a n-dimensional partial order in some higher dimension. And our goal is to map from this category A or database 1 to category B or the database 2. And this thing is called a functor between these two categories. So our deep learning should be able to approximate this functor between these two categories, which would preserve the partial order in some latent dimensions. So how do we do it? So we use bidirectional DB converter. So we have the M is the mapper or the forward converter. So it takes your data from one database 1 to 2. And we have an inverter or backward DB converter. It takes back from 2 to 1. And we train them in tandem. But as I told you that, how do we gonna define the loss? Because we don't have the ground truth at all, right? So I'll give you a metaphor. So some of us may know this meme. Johnny said no is no, no is no, no. So basically this funny translations occurs when the Google Translate fails to translate some Chinese text. But let's say you and I don't know Chinese. So what do? So we take the Chinese text, we translate it into English, and we translate it back to Chinese. And then we see that it doesn't match. So so this is a famous quote, zi zi wei zi zi, bu zi wei bu zi. When we translate it to English, so here the mapper, the first translator, completely fails. And that's why when you translate back, you see something much longer. It's not same, right? We can now evaluate based on this and this. And we should minimize this distance. If they are same, that means that both mapper and inverter are working fine, right? So we use the same idea. So to train the mapper, we first map from 1 to space of 2 back to space of 1. They should be exactly same. But you may say, wait, what if both of them are just identity function, right? Then you would still get the same result. It's not learning anything. So we also train the inverter. We start from the 2, go to 1, and back to 2. And we train them in tandem. How do we design the loss function? So we try to ask the question that what are the things that we want to be conserved? So when it's mapped to one space and back to one's original space, we want the actual locations, in n dimensions to be same. So we used earth moving distance and Euclidean distance. Then we thought the entropy of this database, they should also remain same. The cosine similarity between each variables should be conserved. And we added something called neighborhood topology loss. So the topology should also be conserved. That is to say, if I'm here and someone is healthier than me and someone is less healthier than me, this order should be preserved in the other one. So these two are my neighbors. When I'm mapping myself to another space, those two still should be my neighbor. So we evaluate our method in three ways. First is looking at the distance matrix. So we take one of these data sets, DS, we convert it with the forward DB converter, and we convert it back with the backward DB converter. The color is not good here, but so, and we evaluate in between these two because they should be same. Same for neighborhood checkout index. So what we do is in same way, we compare in between these two, and also we do the other way around. So let's say we make a PCA plot of database one, this principal component one and two, and now when we map them into the database scheme of database two, let's say it looks like something like this. So they move around because it's a new space. When you reconvert them, those light green dots, they should actually fall on where it originated, right? And based on this, if they are in the same space, then the neighborhood should also be same. So we ask if the top 5% of the population's neighborhood is that same for what you start with and what you end up with. And we calculate a Jaccard index based on that. So here's some of the results. So we start with DS. We make DS into the share scheme, the EU data scheme, back to the German data scheme. And you can see this one patient number 271, he moves from here to here and back where it started. Similarly, we see this for when we start from the EU scheme, go to German and back to EU scheme. So that means that we can now convert your data from one database scheme to another. We also do something called cross-cohort validation. So you remember in the beginning I said that if you had a model trained in, if you have one data and a model trained in that, can you use it on the other data? So we have, for shared data set, we have something called the physical inactivity variable, which is binary. And this can be predicted on the other variables, and we already have a pre-trained model for that. However, for DS, we actually don't have this particular variable, but you might be interested to know what would be the physical inactivity of the people who goes to DS, right? So we can do the conversion with a forward DV converter. We go to the DS scheme now. So we have the converted physical inactivity. Now, if we don't use this converted physical inactivity, we use the other converted variables, push it through the pre-trained model, we should get a predicted physical inactivity, right? Now, if our conversion worked perfectly fine, and if this pre-trained model is good enough, then this predicted physical inactivity and the converted physical inactivity, they should match. And we see they indeed match. So it means that our data conversion is actually working and it's good enough to allow use the existing models. Now, in terms of numbers, so the first one is on the synthetic data. So our L1 error, or the earth moving distance, is always 10 times better than the random. So we are always better than any random conversion. The same for the categorical. Now about the neighborhood Jaccard index. Now neighborhood Jaccard index works really well when it's the continuous data, but you'll see the performance is a little less when it's a categorical data. It's because when you make the categorical data, you can see in the PCA, many dots are falling on the same position. So then top 5% doesn't really make much sense, right? However, we know that it's still good is because we have seen in the cross-cohort validation, it's still working. and we see the trend, similar trend in the real data. Now, this DB converter is something that we all can use for different kind of database you have and you want to map. We deploy it in Google Colab format, Python executable file, and also as Docker. So if you go to the GitHub, you'll see that you can change the input and output of two neural networks. So one thing that has to be same is your mappers in output should be your inverter's input side. So those things you have to make sure. You can change the hyperparameter input data and output directive paths. So inside the source code, you see model.py. It has two classes. One is for the forward DB converter or mapper, and another is for the inverter or the backward DB converter. Based on what kind of data you have, how big is your input and output size, what the number of variables, you might need to change them. For now, is just a fully connected neural network with prelude, batch norms, and some dropout layers. One important thing that however I design the mapper, my inverter is just flipped version of that. And we have the main.py where if you run it, it would run the whole training and also the inference. Or if you already have a trained model, you can run the inference.py and it would only do the inference. Inference part is the data you give it in the test set, it would give the converted versions of them. So DB converter can make two databases compatible if they're designed to measure the same underlying reality. And I would like to thank my collaborators, my PIs, and this is the link for DB Converter. And let's get connected in LinkedIn if you have any questions.